Hello guys, welcome to Physics Grad. In this video, we are going to continue studying about some more important properties of the Lagrangian function, which we have already seen in the previous video. So, in this video, we are going to study two more important properties of the Lagrangian, and that is the additivity property and the non-uniqueness property. So first, let us consider the additivity property of the Lagrangian. So consider two subsystems. So subsystems which are not interacting. So what do I mean by this? So for example, you can consider two particles A and B separated by some distance, and when I say that they are not interacting, what I mean is that there is no force of gravity between them, or if there is any, it can be safely neglected because it may be very, very small. Similarly, no Coulombic interaction, and so on. So there is no interaction between A and B whatsoever. What it means is that A does not exert a force on B and B does not exert any force on A. So it doesn't exert any force on B, neither does B exert any force on A. So that is the meaning of non-interacting particles. So another way of saying this is that the motion of the particle B is not affected in any way by how particle A moves. Okay, so non-interaction implies motion of B is not affected by motion of A, and of course vice versa. Okay, so that is the meaning of non-interacting subsystems, which in our case are just two non-interacting particles. Okay, now let A be described by the Lagrangian LA. So similarly, let B be described by Lagrangian LB. Then we have, how do we calculate the path which is traversed by the particles A and B? Well, from the principle of least action, we know that the correct path for A is the one which corresponds to the action for A taking the minimum value. So when I minimize this particular action variable for the action integral for the particle A, then the condition corresponding to that dictates the path which is taken by the particle A, or in other words, it characterizes the motion of particle A. And similarly for B, we have the corresponding action integral defined as T1 to T2 LB dt. Okay, so since they are non-interacting, the motion of A should not be dependent on quantities which describe the motion of B. Okay, so therefore, since A and B are non-interacting, the quantities which define motion of A should be independent of quantities which define motion of B. Okay, so that is the meaning of non-interacting particles or subsystems. Now, if you consider, if you consider the system which is A plus B, or the two particles taken together now forms one system, then how will you characterize this particular system mechanically? So, how to characterize this system mechanically? The obvious answer is that we need to get, or we need to define the Lagrangian for this new system. So we need the Lagrangian for A plus B. So what is this Lagrangian going to be? So because of this region, LA should be independent of LB, or in other words, the quantities which define LA should not appear in quantities which define LB. Okay, but when I consider the motion of the two particles as a whole, then the Lagrangian of this particular system must depend on the quantities which define the motion of A and the quantities which define the motion of B. But since LA and LB alone do not contain all of these quantities, we need to somehow include both of these Lagrangians, which are LA and LB. And the most reasonable way of doing that would be to say that LA plus B should be equal to LA plus LB. Now, does this make sense? So why does this make sense? So this is because of the following. So if you consider the action integral for the entire system, it will be defined this way. Now, the correct path which is followed by A and B will correspond to this action taking the minimum value from the principle of least action. Okay, and that path will be defined by the equations of motion for both the particles A and B, which in turn are derived from the Euler-Lagrange equations. Now, if you consider the motion of particle A alone, then the Euler-Lagrange equations will apply for the Lagrangian LA. And if you consider the particle B's motion alone, then the Euler-Lagrange equations will will only be the relations with respect to LB. But here we need to incorporate the motions of both the particles. So that is why this definition is going to work. So let us see what will happen if we substitute LA plus B with LA plus LB. So this will become integral T1 to T2 LA dt plus integral T1 to T2 LB dt. Okay. So the way the particles move will not know whether I am considering only this as a system or only this as a system, or whether I am considering the whole thing as a system. The particles do not know that. The particles will move according to the equations of motion, which are in turn governed by the Euler Lagrange equations for these individual action integrals. So therefore we should end up with the same set of conditions for the motion of particles when we consider both of them as a whole. So that means the same set of conditions which are separately satisfied here must also be satisfied in this case. And the only logical way to get this would be to simply add the two Lagrangians, as the Lagrangians for each of the particles will be defined by quantities which are independent of the other particle. So when we minimize SA plus B, we naturally have to minimize this quantity as well as this quantity, which leads to the corresponding equations of motion. So this gives SA plus SB. And minimization of SA plus B is same as minimization of SA and minimization of SB, which in turn gives equations of motion for A and B. So this part will give the equation of motion for, when we apply the Euler Lagrange equations for this part, we will get the equations of motion for A, and when we apply the Euler Lagrange equation for this part, we will get the equations of motion for B. So therefore the Lagrangian for a system of non-interacting, so you can say system made of non-interacting subsystems, is equal to simply the sum of the Lagrangians of all the subsystems which are non-interacting. So that is important. It should not be interacting in any way. Okay. So this is the additivity property of the Lagrangian. So this is the additivity property. Okay. So what does it say? When a system can be subdivided into smaller non-interacting systems, then the Lagrangian for the entire system is nothing but the sum of the Lagrangians for all the individual non-interacting subsystems. Okay. Okay, fine. Now let us go to the second property that we are going to study today, which is the non-uniqueness. So let us say that we find that a system, so let a system, okay, be described by L. Now I am going to define a new Lagrangian L dash, which is given by some constant A times L plus some constant B. Okay, so this and this is a constant. Now obviously the mechanical state of the system is described when the action integral corresponding to the Lagrangian is minimized. Okay, now the action integral corresponding to L dash, which I am going to call as S dash, is nothing but integral t1 to t2 al plus b dt, which is nothing but a times integral t1 to t2l plus integral t1 to t2b dt. I missed a dt here. So this is nothing but a times s plus b times t2 minus t1. Okay, so we have s dash is equal to a times s plus b times t2 minus t1. Now this is a constant, right? And minimization of s dash is same as minimization of s, because this is a constant. So that means, so minimization of s implies variation of s dash should be equal to 0. So this also implies variation of s should be equal to 0. So this is because of the fact that, you know, any curve which at the maxima or the minima will have its derivative as 0. So when s dash or s takes its minimum value, its variation is going to be 0. And the variation of s dash going to 0 is same as saying variation of s going to 0 because of this relation. So if you see the Euler-Lagrange equation corresponding to s dash and s, so the Euler-Lagrange equations for s dash will be basically what? D by dt of dou L dash by dou Qi dot, okay, minus dou L dash by dou Qi is equal to 0. So this is nothing but d by dt of dou A times L by dou Qi dot, so A times L plus B, minus dou A times L plus B by dou Qi equal to 0. Now since B is a constant, this simply becomes A times d by dt of dou L by dou Qi minus A times dou by dou Qi times L equal to 0, which is nothing but, so this is nothing but A times d by dt times dou L by dou Qi minus dou by dou Qi times L equal to 0, and this implies d by dt times dou L by dou Qi minus dou by dou Qi of L equal to 0. But this is nothing but the Euler-Lagrange equations, Euler-Lagrange equation for the Lagrangian L. Okay, so the Euler-Lagrange equation for L and the Euler Lagrange equation for L dash, or for S dash, or this is same as saying L dash, give the same condition. So both give the same condition. So therefore Euler Lagrange equation for L dash and L both give the same condition, which implies same equations of motion. This implies it doesn't matter whether we describe the system, so system, using L or L dash. So both description gives the same equations of motion. So I can say that the Lagrangian for the system can be L or L dash. So this implies Lagrangian is not unique, because it can be multiplied by any arbitrary constant A and added with any arbitrary constant B. Okay, and I will still end up getting the same equations of motion. So therefore the Lagrangian for a system is not unique. I can also define, so I can also define L dash as the original L plus the derivative, total time derivative of some function which depends on the generalized coordinate and some time. Okay, so if I define the new Lagrangian in this form, let's see what happens. So S dash will become integral t1 to t2 L dt plus integral d by dt f of qt dt from t1 to t2. So this is nothing but S plus, so what happens when we integrate this? So there's a d by dt, so integral of the differentiation of a function will give back the function, and since it's a definite integral, we have to substitute the boundary values, and therefore this will simply become f of q of t2 comma t minus f of q of t1 minus, sorry, this is t2, this is t1. Okay, so S dash is now equal to this. Now to get the equations of motion or the Euler Lagrange equation, S should be minimized, or in other words, variation of S dash should be equal to 0. So what is variation of S dash? So variation of S dash is nothing but variation of S plus variation of f of q of t2 to t2 minus variation of f of q of t1 comma t1. Now, so if you remember from the previous video, the variation of f, okay, so if you consider the video lecture from the math series on Euler Lagrange equations, there we defined this variation of f as some epsilon eta, some epsilon times another eta. Okay, so where eta is some arbitrary function of t defined in such a way that eta of t1 is equal to eta of t2 is equal to 0. So this was how we defined this function eta. okay, and epsilon is of course some number, so some number close to 0, okay. Since we defined eta in such a way, okay, this means that the variation of the function, so this corresponds to, okay, so this will correspond to delta, so variation of f q of t2 is same as writing dou f q of t2 by by dou q, okay, times variation in q at t2. So variation in q at t2 is basically 0 because of this definition. So if you did not understand this part, I suggest that you watch the video on the Euler Lagrange equations, which is basically from the maths playlist, lecture 1. I would advise you to watch this because all these definitions are in there, and what I'm trying to say here will make more sense if you watch this particular video. Okay, so having said that, the variation of s dash going to 0 is same as this particular quantity going to 0, and because of the way we have defined the variation, we have defined it in such a way that the variation at the endpoints go to 0, and this particular case is having the function value at the particular endpoints corresponding to t2 and t1, and therefore the variation of the function at these endpoints must vanish by definition, okay. So this will go to 0. So this implies, so therefore del s dash equal to 0, or variation in s dash going to 0 is same as variation in s going to 0 because of this, okay, and these both terms go to 0. So variation of s dash going to 0 is same as variation of s going to 0, and this is obviously going to give us the equations of motion, because when variation of s goes to 0, s is getting minimized, and minimization of s implies Euler Lagrange equation for s, for the Lagrangian corresponding to s is satisfied, which means we get the equations of motion. So we get the same equations of motion for both s dash and s, or in other words, we get same equations of motion for L dash and L, where now L dash is nothing but the original Lagrangian but added by some total derivative of a function which depends on the generalized coordinate and time, okay. So to summarize, I can define L dash as some constant a times L plus some other constant b, or I can have L dash as L plus some total derivative f of qt, or in general I can have L dash is equal to al plus d by dt f qt plus some constant b, and the equations of motion corresponding to L and L dash, as we have seen, will turn out to be the same, and therefore it is equivalent to describe a system by both L and L dash, and therefore the Lagrangian for a system need not be unique, and this is the non-uniqueness property of the Lagrangian. So that was the non-uniqueness property of the Lagrangian. And yeah, that's it for this video. Thank you for watching. See you next time.